Welcome back to Into the Impossible with your host, Brian Keating. Today we're going to journey through the galaxy and even beyond our solar system with a phenomenal educator, thinker, and scientist, David Kipping, a professor at Columbia and host of the Cool Worlds Lab podcast and YouTube channels with nearly 1 million subscribers and close to 100 million views. David's a renowned exoplanet hunter and author of numerous groundbreaking papers on a subject he basically invented, exomoons. We'll uncover his quest for Kepler 1708 b, a giant moon candidate orbiting a distant world. And we'll explore how our moon and exomoons may help solve the fine-tuning puzzle of extraterrestrial life. David's a remarkable mind, and you'll discover how Bayesian frameworks, birth-to-death ratio rates, and ecological models can converge to challenge our understanding of life in the cosmos. Buckle up for an enthralling conversation on exomoons, abiogenesis, and the Fermi paradox, and learn from David, one of the most renowned educators of our time, why your future cosmic perspective may cause you to see our moon in a very different light. Let's go. Welcome everybody to what promises to be an out-of-this-world experience, a journey through the cosmos, through life, through meaning, and through the origin of it all. And I'm joined with a real, kind of distant friend we just met, Professor David Kipping at Columbia University, host of the Cool Worlds Laboratory podcast on podcast platforms, obviously on YouTube as well. Phenomenal channel, big inspiration. And he's out today to give a fascinating colloquium at the newly formed UCSD astronomy department. Welcome, David.
Honestly, it's a pleasure. I've been watching your podcast for a long time, and I've been really looking forward to visiting and getting to chat to you about this. So.
We've been, number one guest after Elon. Everyone wants to have Elon. I had him on for 10 minutes.
That's a high bar.
Come on, dude. That's right. Well, you're here today to talk about something I find really fascinating. Which is moons and the exomoons, which is, kind of even one step before. I mean, when I started graduate school, there were no exoplanets known for sure, just around the time the first ones were discovered. And now we're talking about exomoons. Yeah. And I want to talk about life, especially today. So important to, us as a species to contemplate if we're alone, if we're not. As Arthur C. Clarke, the namesake of this podcast, who coined the term Into the Impossible, said both outcomes are equally terrifying. Yeah. Right? I want to ask you the following question. If we knew for sure, if God, Mother Nature, Gaia, your chancellor, I don't know, if they came and said to you, David, there's no life on exoplanets, is it still worth studying? Is it still a topic worth studying?
Yeah, I think studying exoplanets, one major motivation is indeed to look for life, but it's not the only motivation for sure. And I'm going to steal from my graduate student, Alex Teacher, who used this phrase a lot. He said there's two types of astronomers: those who want to understand the mechanics of how the universe works. Like, what are the rules by which the universe fundamentally plays out? And I think maybe you might fall into that category. And there's maybe astronomers more like myself who are primarily driven by this question of, are we alone? And that's the itch that we've had since we were children, trying to want to answer. Now, if we ruled out still that there was life anywhere in the universe, which, by the way, is kind of an absurd proposition, but I'll play with your idea. But it is obviously, it's almost impossible to prove an absence. That's kind of an interesting philosophical aspect of this whole search. Is the idea of us being alone even a valid scientific hypothesis because it's unfalsifiable? That's an interesting question to ask, I think. But let's just say we played the game that we did get to that point. There's still all the questions we might ask that's still on that more mechanical aspect of how do planets form? How do they evolve? How do they change? What is the chemistry of different worlds? What are the rules by which this whole universe plays out? If we wanted to make a simulation of a simulated universe one day, we need to know how the rules of physics play out and build these things. So just understanding our story. I mean, when we try to understand why the Big Bang happened or how do galaxies form, we're not doing it because we're driven by the question of life. We're doing it because we want to understand the story of the universe. And planets are just as much of an equal part of that story as a galaxy is, as a supermassive star is. So I would say if you take that away, it just puts us on the same footing as all of the questions in astronomy. But the fact we have that on top is just like this giant extra cherry that you put there.
It is really fascinating. I mean, it's the top one or two questions I always get, ask my guests, what's the most interesting thing in the universe, even those that don't study astronomy. And it's, how did the universe come to be? Yeah. And the second one, or the first one for some people, I assume you, is are we alone? Is there life elsewhere? Yeah. What's fascinating about what you do is you really are thinking, 4 moves ahead. You're thinking about the role that moons might play. And in appreciation for you coming out, I actually brought a piece of the moon, the Earth's moon. This is actually for you. This is a fragment of the Earth's moon, which is not delivered by the astronauts. NASA, if you're listening, it's a felony. It's a class 1 felony. Actually get moon rocks from the Apollo program, but this was delivered by gravity. So a meteor hit the moon, destroyed some, made a crater or 2, and then that debris floated out and eventually congealed. That's for you.
That's really. I'm honored. Thank you so much.
I gave one to Joe Rogan, and I think he smoked it. I haven't seen any since. Anyway, but my question is, knowing that the moon plays a crucial role, at least in life on Earth, and the hypothesis in which it formed is sort of coming together. We had James Arnold, who's a professor here, is one of the founding Apollo scientists who worked on the mission. The question of, the role that giant collisions play in the formation of moons, and then the role that moons play in life. Can you walk us through that and how probable it might be, or improbable, that such an event would occur on the moons that you study?
Yeah, I mean, there's this idea of how the moon formed that has kind of become canonical at this point, but still people are legitimately questioning it. That's one thing I like about science, is that nothing's ever set in stone. But the canonical idea is that there was this Mars-sized object that crashed into the Earth. We normally give it the name Theia. And it's interesting to ask where that Mars-sized planet actually came from itself. I mean, the solar system was in the process of forming planets. Turns out when you look at you simulate these collisions, you can't have these collisions happen too dramatically, with too much kinetic energy. Otherwise, it's too destructive and you can actually end up destroying both bodies. So you have to have a fairly gentle impact. So one of the ideas is that Theia may have formed in the same orbit of the Earth at 1 AU from the Sun, but it formed in one of the Trojan points, in a horseshoe orbit. So this means it's kind of librating around this horseshoe position. And essentially, if it's more than about 10% the mass of the Earth, any object there, its librations will kind of compound and build larger and larger. And so eventually, this wobbling got so big that it basically grazed and struck the Earth. And that impact was still extremely energetic. It largely vaporized Theia, but it left the Earth, which would have been larger in the past. It would have been, a super Earth, essentially, at this point. It stripped some of that upper mantle away. That upper mantle then formed the moon, and that's why the moon doesn't really have a significant core. It's primarily just essentially mantle-like material from the Earth. We also know from the Apollo rocks that it has the same oxygen isotope ratio as Earth rocks. That's how we know it really, this used to be a part of the Earth.
That's right.
Went up to the moon, and now it's come back down to where it belongs, back on the Earth. So this impact was, it has lots of interesting coincidences. Like it has to have this Theia type object, has to be just the right mass, has to be a grazing impact, not too hard, and also just the right angle. If you change the angle, you can actually destroy both bodies as well. So a lot of people have tried to simulate these realizations of this impact, but it raises the obvious question as to how often does that happen? And that's one of the reasons we want to look for exomoons, is to hopefully fill out that question. And the presence of a large moon does seem to have some benefits. By that large impact, it's thought, for instance, you may have stripped off a lot of that thick upper lithosphere that was forming on the Earth. And had that not happened, rather than having like a roughly 10-kilometer crust around the Earth, it could be 100 kilometers crust. And that would be so thick that you wouldn't be able to have plate tectonics. You would form a stagnant lid, which is what Venus has. And things do not go well for Venus with the stagnant lid. So, you can't have carbon recycling. You can't have the nitrogen stuff, things like this. So you would end losing subduction and the ability of the Earth to recycle materials, which seems kind of crucial for the longevity of a biosphere.
Right.
So that seems a possible, this is speculative because we can't really redo the experiment, but I think it's a reasonable argument. We also know the moon has a large tidal influence on the Earth. It would have raised very large tides on the early Earth. It used to be a lot closer to us than it is today. Right. It probably would have formed, how big? Probably like maybe 50 times larger in the sky, I would have guessed. It'd be much, much closer.
Yeah, but like 10,000 miles away.
But I'd guess it'd be 30 if I was going to do the math, because it's 60 Earth radii away from us, and it probably formed about 2 Earth radii, because that's the Roche limit around the Earth. So I reckon it'd be about 30 times larger in the sky. And it would have created these large, large tides. And when the land and continents first formed, these tides would have covered the entire land continent with these tides for a period of time. And so it's thought that could be conducive for the emergence of life, because one of the possible places that life could have formed is these little rock pools that, where essentially concentrate chemistry through the process of evaporation. You get these organics forming there. So that could be maybe where life began. And then finally, a third reason to think a moon is useful is the stabilization of the Earth's tilt, which is the thing actually people normally would start with in this argument of three. But yeah, that's been shown in a paper by Jacques Lascar, I think it was 1993, in a famous Nature paper, very well cited. And he showed that, if you were to take the moon away and evolve the Earth's obliquity, because of the influence of Jupiter and the other gas giant planets, it would cause the Earth's obliquity to wander over millions of years. And so you would end up with periods of time where the North Pole was essentially pointed at the sun, and then 6 months later the South Pole was pointed at the sun. It would give you a very different climate. You could imagine maybe simple life persisting, but agriculture, a civilization, maybe complex land life might be harder to imagine.
First of all, let me compliment you further, because your writing is sort of unique for me as an outsider in this field in that it's incredibly accessible to simple experimental cosmologists. Okay, so one of the frameworks that I can kind of translate from when I went to Paris for the first time, I couldn't speak French despite 4 years of high school French. And I remember coming out of the metro and seeing a kid, and he was playing with his dog, and he was calling the dog, and the dog was doing, and I was like, that dog knows a lot more French than I do. But I said, I'm going to read Poincaré because, I understand relativity, and I'm going to get this right, so I can translate your work on Bayesian frameworks into my language as a cosmologist.
Well, I got it from cosmologists. I learned Bayesian statistics from cosmologists.
And I think I think a lot of the early Bayesian stuff came from your past guest and my past guest, Adam Rees, and their team. They kind of pioneered that. We kind of neglect the influence that they had in the supernova type 1A search. But I influenced by you and inspired by you, I decided to do a little Bayesian framework. And of course, I utilized my research assistant. Her name is ChatGPT. And I asked the following question. If we know that the moon and even a Mars rock, which I have, which when you come next time or I come out to visit you, another girl, bring the Mars rock.
A good reason to visit again. Just keep collecting all this swag.
Well, there's one more piece of swag I'm about to give you. So we know that this rock came from the moon, and other rocks came from Mars. Given the fact that occurs in that direction, it certainly occurs in the reverse direction, namely that the Earth has been bombarded by objects like this. This is your second gift. Let me, before I give it to you. So these are, of course, meteorites, which I collect. This one's from Argentina, and I do give these out to any member of the audience in the USA who has a .edu email address, and I give them out to other people too at briankeating.com/edu or /list. I'll give it to you, our students. We'll get someone I can visit you. So this material came from space, but the inverse process where Earth gets bombarded and its material goes onto Mars, that surely has occurred even over the period of the bombardment periods that you know much more about than I do. And during the period of time in which Earth had life on it, you've talked in recent videos about how, fecund and how vital and how rapid life could have originated on Earth, even if it was brought from elsewhere. So that means for billions of years, Earth and Mars have been exchanging material. And in particular, life, and we know that extremophiles from, past guest and friend, I'm sure you know Jill Tarter, life finds a way, as Jeff Goldblum said in Jurassic Park. I'm asking the following question, or I asked ChatGPT. I only get. What's the probability that you wouldn't find life on Mars? Just given that life exists on Earth, we're in very similar orbits, both habitable zones roughly, right? I asked, and it's actually, it seemed to be fairly probable. And obviously, you're going to do a much better analysis than I do. But what do you make of that argument? Is it not possible to say that we should be able to use this to constrain a little bit of the prior on how likely life is to evolve once there is life in a solar system? Does that question make sense, or is it?
Yeah, so
I know it's not going to be like, of course you can't prove the negative, as you said, but doesn't it give us some, Bayesian credence value narrowing? What
is the probability that Mars does not have life, and that life would have shared a common ancestry with Earth?
Yes, it will stipulate that life originated on Earth, and then it's made its way through panspermia, which is, sounds dirty, but it's not. Fred Hoyle, who used to come to this very office to visit Jeff Vervich. The question is, so that if life is so, easy to spread and so rapidly proceeding, given that we've been exchanging, we've been sending care packages to Mars for 3.5 billion years with life on it. So what the fact that we don't see life on Mars, at least yet, we haven't searched all of it, but we don't see obviously technological life. Can we not set a bound on the prior that of how difficult it is to kick off life on another planet?
Yes, I think, if you were to prove a negative on Mars, then there's two interesting consequences. One, it would basically mean, maybe panspermia, even between two neighboring planets, is not a very efficient process of this taking place. And I think there's lots of credible reasons why one might be skeptical of that being effective. These rocks don't necessarily do a direct route, right? It's not, if you fly on, Starship or something, maybe it would be like an 18-month trip from Earth to Mars, which is about as fast as we can go. But that's, a coordinated Hoffman transfer orbit. You wouldn't expect that a random rock knocked off would necessarily follow such an efficient path. So I don't know what the typical timescale would be, but I can imagine these rocks spending millions of years out in the abyss before they eventually make their way to one of these planets. And then the question is, how long could a spore of life truly survive in the vacuum of space? Now, we've exposed things like tardigrades and bacterial spores to the vacuum of space, and they have survived days, weeks, I think even months in the vacuum of space and be reanimated. I don't think we can do the experiment where you simulate what 1 million years of that environment would be like for such an entity. So I think it's an open question as to whether it's really plausible. And of course, if you go really long, if you go to billions of years, like potassium, which is a key part of a lot of our chemistry, decays on a 1.3 billion year half-life. So a lot of your elements will actually start to, and carbon, has a 6,000 years, carbon-13. So, some of your actual elements, if you're just hanging out for a long time, would actually start to degrade. So that there must be a time scale which, no matter how well adapted you are for space, and it's kind of, obviously these things did not evolve to be well suited for space, they're just hardy, there must be a time scale over which they cannot survive that journey. And so I guess the real question would be, how long do these rocks typically spend in the environment of space? And then what fraction of those then can survive the impact, which is going to be another, extreme event for the rock to experience and for any life forms to experience that are attached to it. And then once it's done both of those things, it then has to actually have, metabolism and a food source and the ability to respirate and to survive on that planet. So I think there's several steps there where you need like 3 miracles almost to happen. I'm using it kind of playfully a little bit there, but you need 3 things which are not obviously easy to happen to take place. And it may be that those things take place quite frequently, but we certainly have no evidence to support that. And I think I could very well believe that this process is not particularly common. I think one of the things I've been most fascinated about with panspermia, which has changed track a little bit, is with like Oumuamua and these interstellar asteroids that we now, like Borisov as well, that we recently detected. And they are super intriguing because we used to think the idea of interstellar panspermia was an incredibly remote and implausible thing to consider. And then with Oumuamua, we're realizing that actually the rate of interstellar interlopers is orders of magnitude higher than we previously thought reasonable. And that really opens the door because, if Oumuamua is flying through the solar system, some of those Oumuamuas probably hit the Earth in the past. And they could have transferred life from an entirely different solar system, which could have had a 5 billion year head start
in
RNA. Right. So, and that's intriguing. And I know folks have, tried to rewind the clock of, there was a paper I talked about in one of my videos on Luca, the lowest universal common ancestor, which existed 4.2 billion years ago. They were able to date it to. And the Earth only really had oceans 4.4 billion years ago. So within 200 million years, you don't just have Luca. They show that there's a strong evidence that there was an entire biosphere at this point. There was a colony and many, many interacting genomes that were going under horizontal gene transfer with each other. So there was not just one single thing even then. And so it does seem almost implausibly fast how life got started. And panspermia, be it interstellar or from Mars, it certainly removes some of that tension a little bit. It makes it maybe easier to believe how such a complex organism could have evolved so quickly. So it's very intriguing.
So in your recent, you had a recent paper on these 70 cool giant exoplanets and their possible moon surveys. So that was a paper, we'll link to it, Exomoon survey of 70 cool giant exoplanets. and the new candidate Kepler 1708-B1
Just rings off the
just
exactly the tongue.
Yeah, exactly. Yeah, don't judge a book by its cover. So talk about that. What was the kind of science behind it? How did you obtain time and data, and what is the methodology and specific techniques that you, and don't be afraid. My podcast, maybe I'll say, is the brightest in the multiverse. So don't be afraid to get super, super deep into the technology of what you used and how you did it.
I've been looking for moons for like 15 years now in my career. It's been, something I'm well known for, and it's haunted me to try and do this search.
I have to stop you. You say something like that, I have to stop. What is it about moons that is so fascinating to you? Is it our moon? Did you have some experience with our moon? Or
yeah, to backtrack, I got really fascinated into this because almost by chance. I think, obviously when I was a kid, space and the planets were fascinating, like many kids to me. And I remember having this annual of the book of all the planets and all the moons, and just being astonished by, these photos from Galileo and Voyager of these distant worlds that were so alien and so different. You look at a picture of Europa or Callisto or, Saturn, and you're just like, wow, like this is real. This is really out there in our own backyard. So I think, for me, it's always been obvious that moons were kind of the most diverse and terrestrial-like, and that made them more interesting to me. But yeah, I kind of stumbled into moons a little bit by chance, and that was really because I was writing a paper on the transit. I was calculating the transit duration. So how long does it take a planet to transit its star? Mm-hmm. And I was trying to come up with a closed-form solution for this problem. It's just a geometry problem. I'd made the first attempt of doing this with an eccentric orbit. Before then, everyone had just done it with a circular orbit, which seemed reasonable because the planets in the solar system were mostly circular. So everyone assumed exoplanets would be the same way, right. But we were starting to get hints that actually exoplanets can be quite eccentric. So I generalized the calculation. And then I think the referee asked me, or maybe I was thinking in my head at some point, like, what could make this calculation be wrong? Like, where would one of my assumptions be false? And one of the assumptions was, this Keplerian orbit. One way to get a non-Keplerian orbit would be if something was wobbling it. And so that's where I started down this path of thinking about the moons and how that would change things. And that got me excited because whenever you find a way to basically prove your idea is wrong, that becomes a way of detecting that thing.
Right.
And so I started down this path, and I just...
That's really important. I have to pause you again. You're giving me too many good nuggets here. So I always have to kind of double click on things that are of interest to young scientific researchers. Yeah. And what David just explained, as a general principle, when you see a flaw, I would say a flaw can lead to a new law. And that's exactly what you did. I mean, the Earth is an anomaly, as I understand it, in our solar system. Certainly it's the only planet with one moon, right? And so you're thinking there could be some wobble, there could be some, and that could come from the fact that, like most stars, maybe most planets have multiple moons.
Yeah, exactly. I mean, and it's really just an extension. I mean, there's...
in the planets themselves.
There's looking for a flaw in your theory, to pick up on that piece of like, this is a new thing we can look for. But then there's also analogizing. So you can take the analogy of, okay, we are detecting lots of planets by looking at wobbling stars. That was the primary method at the time people were detecting planets. And so this is really just an extension of that. It's saying, well, let's just take that same principle and apply it on a smaller scale and see what falls out. So yeah, I really love talking to colleagues in other fields and other disciplines, cosmologists, but also, totally other disciplines like chemistry and biology, because you hear about the way they are thinking about problems, and you see so often in science that the way problems are solved are transferable. Maybe you change the scale, maybe you shift an axis, but it's a lot of the same things being discovered multiple times, which are really just mirrors of each other. So yeah, I took that idea and kind of ran with it. And I think personally, I just realized it wasn't, I liked moons a lot, but I really just liked new ideas primarily. And I realized at the time that I had a choice. I had kind of a fork in the road. I could either keep working on new ideas, and certainly I do keep working on new ideas, but I could just totally leave the moons behind and just let other people figure it out. Or I felt like I had head start. You're in a race to find the first whatever, and by virtue of all this modeling work I did, I knew I was probably the person, it sounds a little bit cocky, but I knew at the time I was probably the most, I'd probably thought about Exomoons harder than anyone else, and so I had an intellectual head start. Yeah. And so if anyone was going to do it, I probably had an advantage. I had an ace up my sleeve to pull that off. So I thought, yeah, and it's a bit of a risk. And I remember a colleague saying to me, I remember at a cocktail party, an esteemed professor at MIT said to me, David, why are you doing this? Like, why don't you look for hot Jupiters? They're everywhere. they're really easy to find. Like, you can write so many papers. Why are you trying to look for moons? You're not going to publish any papers. And I knew rationally what he was saying made sense from a career perspective, but it just didn't excite me. To do something that had been done 100 times over just wasn't as exciting as doing something that had never been done. That fresh snow, it's like going out to the piste and you've got 2 tracks. You've got the heavily plowed track and you've got that fresh snow. I'm going down the fresh
It's
snow.
so funny because I make this point in my first book about Galileo. So he didn't invent the telescope. We know that. He had an incredible amount of success, like you. I'm going to compare you to Galileo with moons as well. He discovering the moons of Jupiter, which he decided to name after his funding agency. The Medicis. He was smart. But when he discovered it, he realized, if I make these telescopes and give them away or even sell them, I'm going to be out of business. I won't be able to make all the discoveries on the fresh snow as David just spoke about. So instead, he published the instruction manual without the equipment. So it's kind of the opposite of what we do now. Now we put out an iPhone, no instruction manual is needed. But he put out the Sidereus Nuncius, and that just showed what you can see if only you had it. And he even denied it to Kepler. He didn't let him use it. So it's a very brilliant thing to do as a scientist, to see when you can make a new contribution, even if you're older, gray-haired colleagues don't recommend it, right? So this is a way that you can make progress. Being the first has a monopolistic advantage sometimes. So how do you know when you've seen an exomoon, for example?
Yeah, so in this, maybe to come back to this paper, the way we are looking, there's many ways to look, but the way I think is the most plausible way of getting a success is to look for transiting moons. So transiting planets is the most successful method we have of detecting planets.
That's Kepler's.
Yeah, so this is things like the NASA Kepler mission. And before that, there was this European mission called Corot. There's also many ground-based surveys called like WASP, HatNet, TRACE before that. So there's a whole bunch of these surveys looking for planets. We're using that same technique and we're piggybacking off that success because A, they've already taken huge amounts of data. So we don't have to build an Exomoon telescope. The data's already been taken in all these telescopes. And B, we know this technique is incredibly precise. So the smallest exoplanet detected is about the size of the moon, transiting a star. So we know moon-sized planets are detectable with this method. And if a planet has a moon, then as it transits in front of the star, it causes, of course, this dip in light, a very tiny dip in light. And if there's a moon, it will cause next to it, either before or just after, or maybe right on top if you're unlucky, but it will cause an extra dip in light. And it's that extra dip we look for. And obviously that extra dip will be transient in its location. That makes it a little bit harder. With a transiting planet, once you've got the period, you know exactly pretty much where it's going to be every time. So you go to the telescope, you can really predict and dial in exactly what it's going to be, and you can stack all your data and get this kind of binning effect to build up the signal to noise. We can't do that with exomoons. We can't stack data in the same way. And so that has been one of the challenges of looking for this type of signal. And of course, also it's a very small signal. You look at the moons in the solar system, the biggest moon is Ganymede. And Ganymede, I think, is about 2% roughly the mass of the Earth. So it's about 40% the size of the Earth. But, even though that sounds good, 0.4, the transit signal goes as 0.4 squared because it goes as the square of the radius. So, yeah, that's a small, 0.16, that's a very small signal for us to try and grab.
What are some of the systematic or biases that you have? Do you have a bias effect that you're more sensitive to shorter period rotations or orbits of the moons?
Yeah, generally, moons which are far away from their planet are best for us. All things being equal, so keep the mass equal, the size equal, everything else. If you just change the distance, the further away it is, the better. There's 2 reasons why. One, there's really 2 signals that we're looking for. One is the signal which I wrote about during my PhD thesis, which is this wobble, and that's what really inspired me into this journey of exomoons. And yeah, the moon will gravitationally tug on the planet, and so as Kepler showed, things don't, and really Newton showed more rigorously, things don't orbit a single point, they orbit a common center of mass. And so the planet will undergo this slight oscillation around that center of mass, and that wobble will cause the times of transit to slightly vary. So we call these transit timing variations, or TTVs. For the Earth-Moon system, it's about 2.5 minutes. So I always think it's kind of fun, like an alien seeing the Earth transit the sun would sometimes see the Earth transit 2.5 minutes earlier and sometimes 2.5 minutes later because of the moon. So they would know the moon was there. That's actually a pretty decent signal. Yet more, I think, I'm probably the only person who thinks this, but when we do our sort of calendar of like when New Year's Eve, like when does the clock strike 12? we should really account for that 2.5 minutes.
Moon minute.
We should look at where the moon phases and adjust the time. So yeah, maybe I'll do a New Year's party where we'll
Proxima Centauri and correct for that.
barycentric motion. So yeah, this effect is in there. And then the other effect we look for is just the dip itself, which I talked about, the dip of the moon blocking out starlight. So they give us different things. The dip gives us the size of the moon, physically how big it is, and the wobble gives us the mass. So once you've got mass and size or radius, then you can figure out the bulk composition, the density. Going figure out if it's icy moon, rocky moon, things like this. That's kind of the hope. So yeah, we took this sample of 70 exoplanets and we just scanned through them looking for these signals. And the reason why we did 70, there's 5,000 exoplanets out there.
Right.
Like why do these 70? It's a pretty small subset. We concluded they were pretty much the most likely to give us a success because they are really far from their star. And they're really big. So they're basically like the most Jupiter-like things that we have. And yes, Earth-like planets could have moons, but we can barely detect the Earths anyway. In fact, Kepler found 0 true Earth twins. It's basically just impossible for Kepler's precision to find true Earth twins. But Jupiter's, we have plenty of those. So, plenty, we have about 70. So we figured that would be a nice sample to go after. And amongst that 70, we looked for all of these effects, and we had this one object which really stood out and looked like potentially the real deal.
It's Kepler 70.
That's Kepler 1708b-I.
And you talk about it as a good scientist should, as still awaiting confirmation or needing what would confirmation come from? I mean, we don't know the Kepler right now. So what are you looking forward to in the future for confirmation potentially?
For a particular object to confirm it, we would probably need JWST to look at this object, unfortunately, or another Kepler. You could just build another Kepler, I suppose, to do it. We wrote a paper that actually proved that Hubble was not sensitive enough to detect it, which is surprising because Hubble's a bigger mirror. It's 2.4 meters. Kepler is 1 meter, but the difference is the systematics. So Hubble is in orbit of the Earth, and thus it is corrupted. The data is polluted by many systematics, such as thermal cycling, various sort of instrumental effects with these infrared detectors, which creep in. Whereas Kepler was an optical CCD, so it's a much simpler instrument. It doesn't have any spectrograph or anything on board, so it's just a light bucket, super simple. And so you get really, really precise data, and it does it for 200,000 stars simultaneously. So therefore, you can use those other 200,000 stars to decorrelate and clean your data. So you can do a really nice job with Kepler data. So it's kind of amazing. Like Kepler actually is more precise for that object, at least, than Hubble would be. So yeah, we would need to go back with JWST. We have 2 exomoon candidates that we have proposed in the literature so far. And both cases, you would probably need to go back with one of these supersized telescopes, and you would want to see the transit of the moon. And,
the ground-based terrestrial telescopes, like the Giant Magellan, or are you saying space telescope?
I think you probably, do it from the ground is hard because both of these objects, they take so long to transit their star. So the transit is, I think, around about 20 hours.
Wow. Okay.
So you just can't do that.
0.1%.
Unless you're in the North Pole, the South Pole, right? You can't get a night that's that long. So, yeah, one of the reasons why we use space is because we can observe for more than a rotation period of the Earth. The JWST data that we collected in October was 60 hours. I mean, you can't do a 60-hour time series from the Earth.
No way. All right. How about what was it like to use JWST? I mean, you're one of the, there are more people in the NBA than have actually gotten good most of the time on JWST. So talk about that process and what you gleaned from it that, was complementary or perhaps, in a way, better than some of the previous data sets that you had access to.
It's an honor to get to use this fantastic facility. It's a huge responsibility in a way because it's $10 billion that taxpayers have spent.
I would say it's $10 billion to build it. To operate, it's $1 billion.
Right. And then, of course, that's not even counting the launch cost, which I think the Europeans or the Canadians ate that launch cost. So, yeah, it's an expensive machine. I mean, it's kind of like going to CERN, right, and having full control over the Large Hadron Collider to do whatever you want for 60 hours. It's kind of ridiculous. Like,
I'm not like you're bona fides. I mean, you're one of the most highly cited and recognized astronomers of the world, and they don't know who you are when you propose, right? It's like double blind or triple blind.
It's double blind. I suspect they can figure it out because the target we proposed for this is not one of those 2 previous exomoon candidates, and that was strategic. Both of those exomoon candidates are Neptune-sized moons. Around super Jupiters, and the reaction we got from the community was basically BS. Like, how could you they just couldn't believe that you could make a moon that big. Was even though theorists are very creative and have shown you could make moons that big, in retroactively.
Hey, cosmic explorers, are you ready for some astronomical trivia? Did you know there are only 88 official constellations? And there hasn't been a new one since 1930, after all. But I have over 900 asterisms. That's right, asterisms are tiny collections of stars, not big enough or grand enough to be a constellation, but just as meaningful to me. And you can leave one of your own, a 5-star asterism, whether you're listening on Apple Podcasts or Spotify. When you go to Apple Podcasts, just open our show, scroll down to ratings and review, and tap the 5-star button. Leave your thoughts as well in the review. And on Spotify, you can do the same. You can even give feedback, comments on the show, and watch in video format as well. And you can do me a great, huge, and fast free favor by tapping on a rating of your own and leaving me that beautiful 5-star gleaming asterism that will make Orion's belt shine with envy. Now back to the episode.
But there was no prediction of such a moon.
And neither was there a prediction of hot Jupiters.
Correct. That'll be exactly my response. But, you just have to, we proposed several times with Hubble to go after those moon candidates, and persistently we were rejected. And not only rejected, but ranked very, very low in the rankings. They just really hated our proposal. So we realized we had to change strategy. And so instead of going after those 2 controversial moon candidates, I don't think they're controversial, by the way, but I have to concede that there is controversy around them. We went after a fresh planet, and this planet was a planet I actually discovered myself back in, I think, 2018, and it's called Kepler 167e. And I guess, the best way to think about it is the most Jupiter-like exoplanet we have found transiting another star. I would make that claim. It is within 1% the mass of Jupiter, within 10% the radius of Jupiter. It's on a circular orbit. It's on a 3-year period. So it's about 2.5 AU from its start. And it has a multi-planet system, and its orbit is perfectly circular. It's on the exterior of 3 or 4 rocky planets on the inside. So it really just looks like, this is as close to Jupiter as we could really hope for. And so our intuition and our claim was, if anything's going to have a series of exomoons, it's going to be this guy. And not only should this thing really, really have exomoons, unless we totally don't understand how moons form, because both Saturn and Jupiter have a whole ton of these things. But not only that, but we really should detect them. And so we showed with the simulator of the James Webb data that if you take the Galilean moon system, named after a gentleman here, and inject it into the fake data, there he is. Just over 400 years ago, he discovered the first moon. So we're trying to carry on his legacy. Yeah. That Callisto and Ganymede we should be able to detect. Io, Europa are a little bit too close. Remember we talked about things too close are harder. So we probably couldn't get Io and Europa, at least not yet with the current data. But we think that, Callisto and Ganymede, we really should detect to 95% of injections, we get one of those moons back. So that was our confidence rate, 95% retrieval rate. So that was our pitch. And I think 3 other teams actually pitched to do the same thing. And so, they are all blind. But I would hope, I haven't seen the other proposals, that ours was legitimately the best. And I think that's because we did a huge amount of that injection recovery work of really proving the whole end-to-end simulation of what we think we can get and how we would analyze the data. And I think that's where you get to pull out your ace cards, right? Because I've been doing this for 15 years, so I know all the tricks, right? And I think you can show that off. I think that's probably why I would guess a review would know it was me, because there's not a huge number of exomoon people.
It's another benefit of being monopoly power.
Yeah, and I talk about some cool words and stuff, so people probably know that James Kipping kind of goes together a little bit at this point. Yeah, I suspect they probably knew it was me, but in principle, the double blind that is there to, stop biases against, race or gender or seniority. And so, I'm all in favor of that. It makes the process actually kind of easier for us in terms of preparing that proposal. And we got the time. We observed in end of October. I think it was over Halloween. We were observing like 27th to the 31st, pretty much. It was 60 hours of data. So that's a profound thing. You're looking up at the sky. Obviously, you can't see JWST, but you can kind of roughly see where it would be in the sky. And you can think to yourself, like, it's actually kind of profound that right now there is that little tiny telescope out there, big by human standards, but tiny compared to the cosmos, that is, $10 billion of human effort and labor. And I am pouring all of my hopes and destiny into what it's going to find right now. Others observing. It's a strange thought to go to sleep at night thinking that. And so the first thing we did a reaction video. We haven't put it on Cool Worlds yet. We'll probably eventually show it. We have this sort of plan as Cool Worlds listeners know that we don't want to sort of live, we don't want to do live updates at every little minutia of things in the analysis as we're doing it, because when I'm working on science, I want to be very objective and focused. And I think as much as I love social media, it can be a distraction when you're really focused on a scientific goal of trying to give people what they want or what they hope to see. And as objective as you can try to be, we all are human and we can all be seduced by that. So I don't want to risk getting pulled into that game. So I made the conscious decision that, we'll try and keep, video logs and things of what's happening. Mm-hmm. But we'll show that at the end once we know either way what the answer is. So the reaction video we shot was getting the data for the first time. And, Ben was plotting the light curve, and I could see the point. There's like 1 million points because we take an image every 1.6 seconds of this star, right? Over 60 hours. There's a huge number of points, hundreds of thousands of data points. And so you can see this like plot populating and it's flat. And we're like, oh God, is there going to be a planet there? And then suddenly it dips down and we're like, oh, thank God, at least the planet
it's there.
We didn't screw that up, because
you could blame Kepler.
Yeah, you
mistimed
it, right? You've got a 3-year orbit, right? And you have to hit that 60-hour right in the nail.
Yep.
What if you slightly miscalculated, right? That's kind of the imposter syndrome fear that you have. But like, maybe I screwed up this like very simple calculation and wasted $10 billion.
The man, yeah, exactly. So unfortunately, it's only a fraction of it. You mentioned the dual, mission that you're on, which is obviously, primarily as a scientist, professor, researcher, but also this secondary mission, which is of huge importance, probably reaches more people, than even the highest citation count paper that you have, which is quite high. How do you balance that? And my feeling is that I am more strident probably than you might be, but it's come out. I'm a born New Yorker, not a transplant immigrant New Yorker like yourself. But that's that. I think we scientists have a moral obligation to communicate what we do in terms that the public can understand. Yeah. And we should do that frequently, because any other person, the carpenter who fixes the door in this office, if he were to come in, I said, oh, what are you doing? He said, oh, you can't understand what I'm doing. Like, I'm doing something so special. I took so much training and you want me just to do this? No, he'd be fired, right? Mm-hmm. So how do you react to that? A lot of, our fellow YouTubers like Sabina Hassenfelder, who's a good friend, she said, no, scientists should do what they do, stay in the lab. If they want to do it, they can do it. I say, you're denying somebody the opportunity to give back, to, pay a moral debt in some sense, but also it's really fun to do it. And it's good for the students and it's good for the, scientists to get exposure to it. But what are your thoughts? I mean, do you think we should, it should be part of your JWST grant? You should have some budget, not just you, but you're already doing it. Sounds preaching to the choir. How do you react to that?
Yeah, I think there's two aspects there. Before I directly answer your question, I'll sort of talk about my motivation for doing the channel. I sometimes got frustrated reading scientific articles or YouTube videos or whatever it was, or podcasts that were secondhand material, right? So I want to hear about the Human Genome Project or something, but rather than hearing from the scientists involved directly, you hear about it from a skilled journalist, but it's still, you've gone through a middleman. You've had some kind of Chinese whispers kind of taking place, the game of telephone, as they say. And so I got frustrated with that because I wanted to hear directly from the people in the trenches what was happening and what it was like. And so when I started my channel, that was my inspiration, was I wanted to provide people the voice from scientists themselves. And I think it's important that people hear from the scientists themselves. How else could the public have trust in what we're doing? If we're always detached and removed from them with several layers of protection in between, I mean, you know what it's like with YouTube. The audience builds a relationship with you by watching, and they get to know your doubts and your skepticism and your beliefs, and they get to feel a sort of level of trust that this person is credible, and they're going to speak out when they see something wrong, and they're going to tell you the way it really is, and that's very fresh. And I think there's a real appeal and desire for that. And I think that's why many, such as yourself and other YouTubers, have been so successful with what they're doing. In terms of the moral obligation to do that work, maybe I'm sort of in between you and Sabine in that sense. I would say that any large organization or team, I agree, does have an obligation to share their results and talk about it. But I don't believe that necessarily every single scientist in the team should do that work.
I agree.
There are some brilliant scientists and grad students I can think of who are very, very good at doing that detailed technical calculation work, but maybe they're just very introverted and they do not do well when put in front of a camera. And yes, you can, train people and help them in that journey, but there are some people who just really don't want to do that. And why should they when the other person in the team is excelling at that thing? So I think as long as we have representatives from fields and from teams and from disciplines, then we're serving that goal of trying to share. And by having podcasts, especially, that's a particularly great way, because then you can really bring in people who maybe I'm not in that category, I hope, but not as skilled at science communication as usual. But you, as the host, can kind of guide them through it to make it a more organic and engaging experience.
The most popular, videos are with, people I totally out of the blue, some extremely, accomplished, brilliant theoretical physicist who studies extra dimensions and graviton, in wormhole. It's just like, no one's going to understand that, but they really shine and the audience really takes to it. My sense is there's a thirst for it. And part of the reason is because, and I don't think they should, every grad student should be on YouTube, but I was thinking more of blogs and just, but public speaking is a very valuable skill, as well as I do, that, there's more to being a professor than just being smart, right? There's marketing, there's sale. I mean, Galileo is a master of this. Like he sold his products, he sold his books, but he was also very, very, very wise and knowledgeable and cunning in some ways. One of the things that really appeals to me about YouTube is that it's two-way. We write a paper. Yeah, the two referees, might read it if we're lucky. I've refereed Nature papers where I'm the only referee. It's crazy. But YouTube, we have our favorite, section, the comment section. It's a two-way avenue where they really feel like they can communicate with people. I feel like that is a service that we do owe to the extent that we have the privilege of a platform to extend to. But
yeah, the other aspect of this I want to touch on is, I don't know if you're interested to hear your thoughts on this, is the asymmetry it kind of creates when you become a successful public communicator of science. As I think, we both have had some success in that degree. And it creates what can be, obviously is like the lowest level, like jealousy and envy amongst your colleagues for the fact that you get to have this larger platform. So if I write a paper, we did it in our last video, our research videos never do as well. By the way, I never ever make a research video, less people are going to be interested in them when I talk about, the universe or something. But it's part of our brand that we always have that authentic connection to real research.
Real science.
But it's an incredible advantage that I have if you think about it. So every paper I write in my team, we could in principle at least have 100,000 people hear about it. Yeah. And that's just like by normal astronomy standards, that's ridiculous. Because as you said, like maybe 2 people would normally hear about the paper. And so maybe I overthink it too much, but I worry about the fact I'm creating like an unfair playing field for myself by having that advantage. And also it comes with responsibilities of being critical. So if I want to be critical of someone else's work, which is par for the course in academia, right? Yeah. That's how academia works, is science works by criticizing, by skepticism, and by building upon other ideas and iterating. Right, that's how science works. But if you do that on a platform where you bring in hundreds of thousands of people every day, the scientists who you are criticizing, maybe not unreasonably, will feel very victimized by that process. And I've experienced that. I've had academics write to me really like very upset and offended emails. And
one asked me to take down a video.
Yeah. And then, how do you deal with that? What's that's where I struggle a little bit as a communicator.
No, you're right. I mean, it is sort of this outsized, magnifying glass, which is so funny because, if you told your 20-year-old self, whatever, 20 years ago, that you'd be a podcaster, you'd be a YouTube, you'd be like, what is this? Like, it didn't even exist, right? And let alone also as a professor, you knew what that was. But it's a privilege to have it. And I guess the all we can hope is that we should be allowed, one of my friends talks about an accuracy budget. Like you should be able to talk in public and not be expected to be Wikipedia or ChatGPT. And that, you might get some of your colleagues' things, maybe not 100% perfect. I was talking about loop quantum gravity or whatever, but I'm talking about it with my expertise, which is as an experimentalist. You are looking at it as a theorist in general, and you can assess things, even if it's outside your field, especially all the more so if it's inside your field. I think to be I think for it's like, I think everyone should have a budget of how many complaint emails they write to airlines, but also how many complimentary, emails or chocolates that they give to stewardesses and stewards, whatever they call them, hosts. Because, I think if it's only one way, it does present sort of a bias. So
if you're only critical,
yes,
and you never raise anyone up, you just push people down.
And similarly, if I only champion my students and my research, it's kind of backhanded way of complimenting me. So I do try to highlight people in my collaboration. I just think they're the most brilliant people I get to spend my life with, a large part of my day with, rather. But I think, we shouldn't feel so much pressure that we shouldn't be able to talk about it. Because you're getting attention to their work and you're not criticizing it. You're not doing ad hominem attacks. I mean, I've seen those videos that you do. They're fabulous. And they bring in a whole host of people that would otherwise be completely ignorant of, again, what their tax dollars are supporting. I mean, again, the awesome responsibility that you felt when you're wielding this $10 billion, that was paid for by taxpayers in different countries. And I'm at a public university, but you're at a private, still you get public funding. Yeah. So I think it's good to think that way. And the last thing I'll say about it is it's good for the students and the scientists to learn how to communicate, to do a little bit of what we do with salesmanship and saleswomanship, whatever you want to call it. We have to be convincing. We have to make an argument. We have to have a certain amount of charisma, but yes, not abuse it. Certainly not. And I don't feel like we're in that field. There are people that do a lot of clickbait. Like I told you, I had Neil deGrasse Tyson on news, and I asked my comment section, as I asked for you, what kind of questions, that they want you to answer. And it's all about your stance on woke politics. No, I'm just kidding. But on Neil, it was like, when is he going to get, apologize for being so what? And I'm like, I'm not going to ask him. Like, that's not fair. I could ask him. We did get into it. I mean, I did ask him stuff about gender and his field, but I wanted I wanted him to express his opinion. And Elon Musk, going after. I mean, imagine like you feel this pressure of going after, we're just academics, right? Imagine Elon Musk is like going after you and saying you got this because of the X, Y, and Z. I think the more you can use it to highlight science, to be a champion of science, we're all inspired by other scientists. We stand on the shoulders of giants. And I think what you do is just so commendable because it's well done. I was joking, like people expect if the light's off or the video's off, like we're doing a Netflix special. You do Netflix. I mean, I legitimately thought some of your videos were in a studio, it's so the quality, the attention to detail. And then on top of that, the rigorous science, it's no wonder why it's become so popular. You're almost done 1 million.
I know you asked me about the green screen outside. You don't? Dude, because I have these videos actually like, is that green screen? Like, no, that's just bokeh. Yeah, that's just...
Someone says like, oh, your hair. What do they use to color your hair? I'm like, nothing yet. It's like, it's a big swing. Yeah. So one of the comments that I had, and we have to run to lunch with our colleagues in a few minutes, but I want to ask my final 4 questions. But one of the questions came from a listener, and I always solicit questions on my YouTube channel, Twitter, X. You can find both of us on those platforms. Is about, will the upcoming missions, Jupiter Icy Moons, the JWST mission, the Europa Clipper, will those be informative at all to your research, or are they just kind of be interesting to you as an astronomer, as a scientist, as a human?
Yeah, I think it's kind of in between those two. Obviously, the kind of information that Europa Clipper will catch, which is like in the early 2030s, is going to be incredibly detailed compared to what we get for exomoons, right? So for exomoons, I think all we can really realistically hope to measure is their mass, their radius, their orbit, the basic properties that we often have for exoplanets as well. We are starting... Well, we have already collected the atmospheric data of many exoplanets, and I think we could expect to do similarly for large exomoons in the future if these Neptune-sized moons are real. They certainly would be quite suitable for that. But with Europa Clipper, I mean, you are taking images at sort of meter scale potentially with these close flybys, where you can see individual fragments of ice blocks, moving around. There's absolutely no way that is comparable to what we can do, nor does it give us a huge amount of influence into our observations, because that's all just lost in the noise. I mean, that kind of level of detail. But I do think it informs us in terms of, if we see an icy exomoon, and we could probably tell that because of the mass and the radius. We'd be like, okay, this is likely something that looks consistent with Europa. Then we could look at the detailed information we have of Europa and say, okay, some of the predictions would be maybe you'd get a plume, for instance, now and again. Enceladus in particular has these large plumes quite often.
Yeah.
And so that's interesting because if you scale that up a little bit, and similarly Io often has these volcanic outbursts, If you just scale those up by a factor of 2 or 3, imagine a super Io, a super Enceladus, then we might start to have a chance of detecting those phenomena. Those plumes as they come out would create a cloud that we could detect spectroscopically. So I think we can, again, by analogy, say like, yeah, that what's happening there isn't detectable with our observations, but we can imagine a way of scaling it up that we could get it.
Oh, fascinating. Yeah. So that's another way of, leveraging tools from another. It doesn't sound like it, but as you said, Kepler just had a photometer. It didn't have a spectrometer. Imagine if it had, spectroscopy ability. Again, your dictate of kind of looking for tools from other dimensions. And even though to a layperson doesn't sound like another, spectroscopy is different from, astronomy or, the written from photometry than, chemistry is from gardening or whatever. David, we're running out of time. I always like to ask one final question inspired by the namesake of this podcast, Sir Arthur C. Clarke, who said the following. He said, the only way of determining the limits of the possible is to go beyond them into the impossible. I like to use that as a vehicle jumping off point. We have a lot of young people listening. If you could go back, spend 20 minutes with your younger self, 20-year-old self, what would you tell him to give him the courage to go into the impossible as you've done?
I think maybe stop messing around so much.
What do you mean?
When I was young, I think I was a little bit, well, I was a naughty kid at school, that's for sure. I misbehaved a lot. I was not a very studious child. And I didn't really get serious about my academic studies until I was sort of like maybe 18, 19. And so I messed around a lot. And I kind of, I do regret that a little bit, that I feel like when you're young, your brain is a sponge. And I wish I was more well-read and using that opportunity to just ingest as much as I could. I was reading the biography of Isaac Newton on the plane ride over, and it was talking about how at age 24, during the plague, he basically invented all of modern physics, for like the classical modern physics. And I was thinking like, wow, when I was 24, I was not nowhere near that level of seriousness. This guy was like, and when he was a child, he was already, building water mills in rivers and things at like age, 11, 12 to see how water flows, and was studying it very detailed. And so, I kind of wish I'd applied myself a bit more. I regret how much. I think it's important to have fun and to mess around. But, I think Arnold Schwarzenegger said this once, that every time you're partying, you're horsing around, just remember there's someone out there who is working their butt off to try and get ahead of you. And it is, when you look at graduate school applications now and getting to Ivy League schools, it is so competitive that you really have to, I feel an enormous sympathy for students who are applying to these schools these days. But you really do need to have that kind of, not all your time, but a fraction of your time, you need to be applied and thinking about your future in a more serious way than I think I did. And I think I would be probably more academically well-rounded had I done so. So I kind of regret that a little bit. But at the end of the day, you are who you are, and you can't go back in time and change things. So it is what it is.
It certainly had much of a negative impact on your career today. And I always point out, you don't want to emulate Newton too much because he died a virgin. And that was he called that his biggest accomplishment. We'll talk about that next time. David Kipping, thank you so much for coming on the podcast. It's brief. We have a million other questions from me and from my audience. We'll do a part 2 when you're out here again. I'd love to have you back. And I'm really looking forward to your colloquium today. And we're going to be super nerded out. And I just love diving deep into other fields. And thank you so much for what you do for science.
Hey, it's great. And I hope to get you on my podcast when you come to New York.
That's a deal.
January. Yeah.
Thanks a lot.
Thank you.
If you enjoyed this interview, I know you're going to love my conversation on how Kepler discovered 5,000 exoplanets with Jason Steffen, one of the leaders of the Kepler mission, and its subsequent data analysis. And see you next week on Into the Impossible.